Alright, hello everybody. We're going to look at problem number 1 from the 2018 AP Physics 1 free response. You can just Google 2018 AP Physics 1 free response and you'll be able to find the PDF that has these questions. So if you have not already, let's pause this video and you can use that PDF to read through this problem. Take a few minutes, put your answers down. You should have an equation sheet out. If you don't have an equation sheet with you, that is also easily found online. So you can have it up in a tab to be able to refer to. But whenever you're ready, come back to this video and let's look at this problem. I want to try to explain the different aspects of it. We'll look at the point distribution and just make our way through this 7-point problem. So this is one of the smaller free response problems. There are only 7 points spread out throughout it. The bulk of them are found in 1B, part 1. These actually go pretty quickly at the bottom. The biggest time in this problem is found here in 1B, but let's start with A. So after reading through this problem, we see that we have a spaceship that is in orbit around Earth. The radius is defined as capital R, mass of the Earth is capital M subscript E, and the very first thing we're asked to do is to just draw and label all the forces acting on this spaceship. So this is where how we defined weight or force due to gravity pays off, that it is always towards the center of the Earth. Notice the spaceship was kind of down here in its orbit. It was not up above, so got to be careful there. I'm going to draw an arrow going straight towards the center of the Earth and label that FG for force due to gravity. And I know that that's definitely a force here. It's tempting to try to put some others. You cannot put centripetal force. Remember, centripetal force is just a net force. It's just a result of other forces. We don't show it in a free body diagram. And there is no normal force. There are no surfaces in contact. We're ignoring any kind of friction, we're out here in outer space with our spaceship. So that is actually the answer to number 1. It is just an arrow towards the center of the Earth and force due to gravity. Now, the next part's going to take a little while, and I'm going to try to relate it back to what you can find on your equation sheet. We are asked to derive an equation for the period of the spaceship's motion around the Earth in terms of possibly its mass, the mass of the Earth, its radius, and any various constants. So nothing else. We're not supposed to have an acceleration. We're not supposed to have a velocity or anything like that. Only what we have here. So I'm just going to start on a blank piece of paper for this. We know that we're going to be using some centripetal information here. The only thing for that on your equation sheet is that centripetal acceleration is tangential velocity squared divided by the radius. And that's it. So we also know that we have two objects, one orbiting another here. So gravitational force we can find our equation for gravitational force. So, it's kind of hard to know, where do I get started here? You get started like you always get started in physics. If you have a free body diagram, you're going to be doing Newton's second law. So we look at the sum of the forces, and, we're looking at the net, and that's the centripetal force, kind of that we're looking at. You don't have to show that. I'm just, letting you see it, and F equals ma. And the only force in town is the gravitational force between our spaceship and the Earth. So we can bring our gravitational force equation in right here. And we get this. So we can go ahead and do one thing. We can go ahead and get rid of the mass of the spaceship. That's going to cancel out. We're left with the centripetal acceleration equals the gravitational constant times the mass of the Earth over the radius squared, and centripetal acceleration is v squared over r. We're going to do that. I'm going to now start using the capital R for that because it was defined that way in the problem. And this is what we get. Problem is, period isn't anywhere right here, but we did a free body diagram. We should use Newton's second law and look at this stuff. So as far as period is concerned, let's look at it separately. On your equation sheet, this is the first thing that you have for the period. I'm just going to use it. You may already know something else that would be better to use. I'm going to show where that is created if you already have a way of relating the period to something found in our equation here. But this is what we have, and this makes sense. If you look at this as 2 pi, well, that's 2 pi radians. Well, that is what we traverse going through one revolution. And angular velocity, well, that is the number of radians per second. So we have radians per revolution over radians per second. Radians cancels. You take care of the units. You get that this is seconds per revolution, which is what period is. And this is not on your equation sheet, but you might recall, it's very, very handy, tangential velocity, or a linear quantity, translational quantity, is equal to the radius times the angular quantity, the rotational quantity. So this has tangential velocity, and we have tangential velocity right here. It'll be pretty easy to get it into this equation. So we'll just do a quick little substitution. I'm going to start to use the capital R, and we get this, just cleaning it up a little bit. And I need to be able to get the period into this. And since both have velocity, we're going to solve for the velocity. And when we do that, we get this, which is a way to relate tangential velocity to period. You might have actually remembered this from that unit. The units make sense. We have 2 pi times the radius. Well, that's circumference, so that's the number of meters per revolution. This is the time per revolution. Revolution cancels. Meters over seconds. Well, that's velocity we're working with here. So let's go ahead and take care of canceling out that radius and canceling out the square. So v squared equals gravitational constant mass of the Earth over capital R. And we're going to substitute in. We need to distribute our square. So that'd be 4 pi squared R squared over T squared. We're almost done, I promise. Okay, be very careful. It's easy to try to say that you're going to cancel out that radius and that square, but that is actually not the case here. But we just want to solve for the period. So I'm going to move it out of the denominator. Okay? And we want to solve for it. So notice this is where if you multiply both sides by r, this r cancels, but then we get r cubed. So now to solve for t squared, 4 pi r cubed over g mass of the Earth and the square root of that. And we are finally done with, the biggest time commitment in this problem. We have solved for the period of our spaceship, and we only have the mass of the Earth. We have the radius. The mass of the spaceship actually is not part of it, and we have one of our constants. So we're going to go back to our little question right here, and I'm just going to write this down to be able to refer to it, that the period was equal to the square root of 4 pi r cubed over g mass of the Earth. we are to compare a new period to the original period. If a new spaceship with a different mass, which is greater than the original, it's twice the amount, is introduced, but the radius is the same, it's just a new spaceship. So let's just look up here. This is an equation that solves for the period. So, see little m anywhere? No, we canceled it out. So the answer is equal. And we would write out a sentence just saying that the period of the new spaceship equals the original, since the mass of the spaceship has no effect on the period. And to finish, we bring in another ship or the original and just moves out to a greater radius. The mass and all that is the same, and we're asked to get the new velocity for it due to, or if it is affected by the increasing radius. So let's go back to the work we did before on part B, and we had this right here, that our spaceship's velocity, technically the square of its velocity, is equal to GME over R. So if the radius gets bigger, the velocity is actually going to get smaller. So, and our equation shows us right there. So the answer would be less than. And I don't have my equation right here, but I'm just going to rewrite it. And you could just refer here and just say as shown. And you can point to this, and you make it easy for the reader to see what you're saying here. As shown there, an increase in the radius will cause the velocity to decrease. So, the points for this problem. So, this was actually 2 points up here. It was 1 point for having an arrow drawn straight along this line. It was a second point for having the force due to gravity shown right here. A point was taken away, or there was only a maximum of 1 point you could get here if you had anything else. So for part B, obviously the correct answer right here is a point, but if we go back to our original work, if you used Newton's second law and you related the centripetal acceleration to the gravitational force, that was worth a point for setting those equal. Okay? And then there was another point that was gained by taking period and velocity and relating the period to the velocity. You could do that several different ways. You might have even just jumped right here to it. But if there was a link shown between the period and velocity and how you arrived here, that was worth a point. So 3 points. 1 point for relating these two ideas, 1 point for getting period and velocity involved together, and then 1 point for the final answer. And then it was 1 point for correctly choosing equal and having an explanation, and it was 1 point for saying that the new velocity is less than the original and having a correct response. So that was 2018 free response problem number 1.